what we were doing last time was going through some of these details of this weak formulation that I was telling you about. That in your quiz 4, the last problem that you solved was like an exact analytical solution to a one-dimensional problem, right? And that solution, as I told you, that type of problem, stating the problem in this manner, is the strong form of the problem. So finding an exact analytical solution to this is what we call solving the strong form. We developed this functional based on the strong form in an integral form, and we said that if we can show that this functional, that this scalar value goes to 0 for any arbitrary u bar weighting functions, which essentially turned out to be virtual displacements, then the only way that can happen is if the bracket quantities are 0. So this was the governing equation, this was the boundary condition at 0, boundary condition at L. And that was essentially the weak form statement that we went through last time. We also took that weak form statement and we simplified it or kind of modified it in a manner such that the derivatives on the virtual displacement and the real displacement within this stress, if you remember, we said stress was equal to Cu prime, and stress prime would be Cu prime whole thing prime. So there are two derivatives on the real displacement and no derivatives on the virtual displacement. If we use integration by parts on this term, then, and actually I'm going to start writing some acronyms here that I'll sort of build a picture, a big picture for you, so that you can easily remember how to work between the strong form, the weak form, the energy form that we'll see later today. We are calling this step IBP, or integration by parts, where we shift over one of the derivatives from the real displacement to the virtual displacement. And what we got last time was a principle of virtual work form of the weak form. So there was this original weak form that we wrote out, method of weighted residuals, and last time we derived this principle of virtual work form of the weak form, where we found that this was the internal virtual work, this term was the external virtual work, and the problem statement is still the same, that find a real displacement or a stress function, sigma of x, and find the T0 or the reaction at the left end such that this G functional goes to 0 for all possible U bar functions. And if that happens, then the only way that can happen is if the original governing differential equation is satisfied and the two boundary conditions are satisfied. So we are still stating the same, we are still solving the same problem as we should. We are still solving the strong form of the original problem, the original strong form, but we are just stating the problem in a different way. And last time we had laid out two important things, these two problem statements essentially, in the method of weighted residuals form of the weak form and the principle of virtual work form of the weak form. Anybody remember what was the difference between these two forms? Of course, this functional itself, even though the value will be exactly the same, but the functional form is different, right? This functional form, the method of weighted residuals with functional form, has two derivatives on the real displacement, no derivative on the virtual displacement. This guy has one derivative each on the virtual and the real displacement. So the requirements on the real displacement u of x and the requirement on the virtual displacement u bar of x are different. That's the only difference between these two forms. Last time I pointed out in the method of weighted residuals form of the weak form, since the real displacement has two derivatives on it, we would want that whatever displacement function we find must be h2. And anybody remember what h2 is? Second derivatives should be square integrable. And I gave you an example of a function that was not h2. That was a function with a kink the derivative would be discontinuous at the point of the kink, and a second derivative of a discontinuous function would be a Dirac delta at that point. Dirac delta is not square integrable. So a function with a kink would not be in H2, which makes sense because when we solve our 1D problems, we expect our for a reasonably smooth 1D problem, we don't expect our displacement or the rate of change of displacement, essentially strain, should not have a jump suddenly, right? Unless there is a material interface or something like that. So um, uh, for those forms, MWR forms, the real displacement should be in H2. And the other important requirement is this guy, that the value of displacement at 0 has to be equal to U0. This weak form does not have any mechanism or a mathematical mechanism to make sure that, that this condition is satisfied. So this condition, we have to make sure uh, to pick real displacement functions which satisfy this condition. And as I'll tell you in a little bit, this condition is also called the essential boundary condition, or EBC. But I'll come to that. So those are the two conditions on the real displacement. And at the same time, we see that there is no derivatives on the virtual displacement. So the virtual displacement has to belong to a space of L2, which is square integrable functions, or that is also called H0. Zeroth order derivative has to be square integrable. On the other hand, the principle of virtual work form, it has equal derivatives, 1 and 1 on virtual and real. So the real displacement now can be in H1. Therefore, what this means is that a function, a displacement function which has a kink in it, that is not in H2, but it is in H1. It is in H1 or not? A displacement function that has a kink in it has a derivative. Its derivative would have a discontinuity, correct? Discontinuous functions, are they square integrable? Yes. So a function that has a kink in it is in H1, but it is not in H2. So that function, a function that has a kink in it, would be a perfectly valid function for this form of the weak form, but it would not be a valid function for this form of the weak form. And the other requirement that, as I mentioned, that the displacement at x equal to 0 for this particular problem has to be equal to the given displacement. That again is the essential boundary condition. When we enforce this functional to be 0, that does not ensure that this condition is met. So this condition has to be explicitly met when we pick displacement functions like that. And of course, we added a condition. We removed one derivative requirement here, but we added a derivative requirement here on the virtual displacement. So now the real and the virtual displacement can be picked from the same space of functions, but in addition to that, the real displacement has this requirement. So both of these statements are equivalent. Okay, these are weak form statements of, or the weak form of the problem statement. We haven't really changed our problem one bit. We still have that one-dimensional problem that we are solving that's drawn up there. Some displacement on the left end, some body forces, some traction. We are still trying to find a function for displacement along the length of the bar. So this is just an alternate form of stating the same strong form of the problem. What I will also do is go through some more requirements on the boundary conditions. You're already seeing how you have to be very careful about boundary conditions when we are working with weak forms. And just as a side note here, all of this we are doing right now would be almost very theoretical. All the examples for this particular theory will come in chapter 6 when we actually start picking sample functions for real displacement and virtual displacement. I gave you a taste of that a little bit like last time, where we said that if we are solving this problem, we could pick a stress function as some linear combination of polynomials, the virtual displacement function also as some linear combination of polynomials. And when you make that assumption, then you could plug that into your weak form and try to come up with a small matrix problem where this A coefficients are the unknowns that we are solving for. That's very similar, or actually exactly the same as what we do in structural analysis. So keep that sort of backdrop in mind when we are talking about all of these picking functions for virtual displacement or picking functions for real displacement or stress. Okay. So we'll come to these types of examples in chapter 6, but right now we need to make sure that that we are setting up the right theory. So, all right. On boundary conditions, a couple more fine points are there. We just said that for the method of weighted residuals form of the weak form, what we are trying to solve for is, or what we are trying to find is the reaction at the left end and displacement, which is in the space H2 second order derivative square integrable, such that u at 0 is equal to the given displacement, and as I mentioned, that is what is called essential boundary condition. This boundary condition cannot be met automatically by the weak form. This is something you have to pick. That's why it is called EBC. And in general, what that boundary condition has to be met on gamma d, which in this case is x equal to 0. But as you've seen, for a different problem, the specified displacement boundary condition might be somewhere else, might be at x equal to L. So we need to find T0 and displacement such that G of sigma comma u bar is equal to 0 for all u bar in what space? For virtual displacements in what space? H0, or equivalent, it's also L2. L2 functions in the domain 0 to 1, which is equal to H0 functions in 0 to L. Okay. If that happens, then the governing differential equation is satisfied. This is GDE is satisfied. This is the traction boundary condition at x equal to 0. And finally, we have this condition, which is the natural boundary condition. So yet another nomenclature for boundary conditions. We had displacement boundary conditions, traction boundary conditions. Then we talked about Dirichlet boundary conditions and Neumann boundary conditions. This is also called essential boundary condition, and the traction boundary condition is called a natural boundary condition. And I'm going to call that NBC. This is on. This is at x equal to L. I need some more space here. So this is at x equal to L, or on gamma n. So gamma d was Dirichlet, gamma n was Neumann. But this is just stating the same thing again. I'll come to why we are doing that. And the alternative form, the PVW form of the weak form, find reaction U in the space H1 of 0 to L, such that U0 is equal to the given displacement, such that this entire functional goes to 0 for all virtual displacements in what? In what space? H1, because you can see that virtual displacement also has one derivative on it. So the first derivative must be square integrable. And once again, this guy is EBC, and we also called this part of the integral as, the internal virtual work, WI, and all the bracketed term as external virtual work. So we are still saying the same thing. Internal virtual work minus external virtual work has to be 0 for all possible virtual displacements. Now, in order to further simplify this, this weak form of the problem, you notice that we are saying find the you find the reaction and find the displacement function, which is sort of not completely necessary. If I know the displacement, function, then can I find the stress function? U take derivative of u, that gives me strain, u bar, or u prime is strain, c times u prime is the stress, right? So if I have the stress, I can easily find out the reaction at the left end by taking sigma 0 acting on -1, right? That is the boundary condition at the left end. So we can actually eliminate T0 from this expression or from this expression by doing something. Can anybody think of how to eliminate T0 from this equation or from this equation? T0 is an unknown that we can easily eliminate by choosing u bar 0 to be equal to 0. Okay, we can choose, we did not have such a restriction on u bar. We just said that u bar has to be square integrable in this form, or u bar has to be first derivative square integrable in this form. But we did not say anything else about u bar, and if we choose that, then we have to solve this full functional. But in addition, if we say that u bar at 0, if u bar at 0, if we pick that to be equal to 0, then we drop out this entire term, that this term entirely drops out. Similarly, this term entirely drops out if we pick u bar equal to 0. So we can eliminate the traction, this traction at 0, because if we know the stress function, we can easily find that by further restricting that u bar at 0 should be equal to 0. And the important thing here is that for a problem like this, the one that we have been talking about, we are saying that the real displacement has to be equal to whatever the specified displacement is. For example, if the left displacement is 1 millimeter, the real displacement must be equal to, we must pick functions that go to 1 millimeter at the left end, the real displacement. But u bar is the virtual displacement. We must pick virtual displacements here that actually go to 0, not to 1 millimeter. Okay, because we want to eliminate that term. So and actually, so that's a point that I'll write here. Even if the real displacement u0 is not equal to 0 at gamma d, so we are picking virtual displacement on the specified boundary. On the specified boundary of the problem, we are picking virtual displacement functions such that they go to 0 here, even if the real displacement does not go to 0 here. Okay, and if we do that, then we have eliminated that term from the weak form problem, and what we that simplifies our weak form a little bit, but that also poses an extra condition on the virtual displacement. So we cannot pick virtual displacement from this space anymore. We must add a condition on it that for virtual displacement, we must, for example, from here, the virtual displacement has to be in h0 and it has to go to 0 at x equal to 0. Similarly here, virtual displacement has to be in h1 and it has to go to 0 at u equal to 0. So I'll create, or I'll define these extra spaces. These are spaces that have functions that are in h0, in 0 to L, and very importantly, u bar 0 is equal to 0. Similarly, this other space h1e, that the subscript e denotes that this that this satisfies the what is called the homogeneous essential boundary conditions. That's also something that I'll write down here. So this is a space that is same as h1, and u bar 0 is equal to 0. So this condition is called homogeneous. I think missing an E here. Homogeneous essential boundary condition, which I will use the short form HEBC. So there's again lots of short forms floating around. EBC was essential boundary condition, NBC was natural boundary condition, and now I have an HEBC, which stands for homogeneous essential boundary condition. Why homogeneous? Because we are saying that this has to be 0 even if the real displacement is non-zero. So the real displacement has to be equal to U0. That's the essential boundary condition. That was up here. That's what we said. That was the essential boundary condition. Corresponding to the essential boundary condition, we always pick virtual displacement functions that go to 0 at the specified boundary, which is called the homogeneous essential boundary condition. And let me take a step back here also. You remember when we were laying out this logic of weak form that that this functional must go to 0 for all possible u bar functions that could be picked from a space of arbitrary functions. The only restriction on this space of functions was that these functions have to be square integrable, correct? Now we are saying that we will pick functions, only those functions that actually start at 0. Okay, because u bar at 0 has to be 0. None of the other functions will be, we are not going to pick any of the other functions. And we did that only so that we could eliminate t0 as an unknown, because t0 is something that we can calculate after we know the solution for u and solution for sigma. Okay, we'll see actually some examples of this. Let me see, where were we? Here. So if we do that, we have if we use this homogeneous essential boundary condition, we will rewrite these weak forms without that u bar 0 term. So we are still finding displacement, which has to be, for the MWR form, this has to be in H2 0 to L, such that u0 at the real displacement has to meet the essential boundary condition, and that function has to go to 0 for all u bar in what space? So if real displacement is h2, because of that, the virtual displacement has to be in, there's no derivatives here, so h0. But in addition to that, we are also saying that u bar of 0 has to be 0. So it has to be in this space. That has to be in space H0 E for homogeneous essential boundary condition in 0 to L. Such that this entire functional goes to 0 for all possible u bar in this space. And note that in this functional, that u bar 0 term is not there, because that is something that we can calculate after we know the solution for displacement. Couple of important things here. Note that this H2 0 of L, this is the space of functions for real displacement. Real displacement u of x, and this H0E, the subscript E, is that comes from homogeneous essential boundary condition. This is the space of functions for virtual displacement function u bar of x. Okay, and this is the new method of weighted form of the residuals form, where we have eliminated the boundary condition at 0 because we can find it as an after fact. or the equivalent PVW, the principle of virtual work form of the weak form, where again we are saying find the real displacement. Note that real displacement will have only one derivative now. So in that case, find the real displacement, which would be in the space H1, 0 to L, such that the essential boundary condition is satisfied and that this functional goes to 0 for all u bar in what space? U bar has one derivative, so it has to be H1, definitely, between 0 to L. Something else? E. E, because in addition to being in H1, it has to have the virtual displacement go to 0, and that is the space we are calling H1E. So once again, this is the space for real displacement, and this is the space for virtual displacement. So it's a very fine, very small, minute sounding point. What's the difference between H0, H1, H2, right? But it makes a huge difference. If you pick the wrong space of functions to approximate your real displacement and virtual displacement, the numerical solutions that you would get from that would be garbage. And and really it's that important because so we all heard that computer simulation was was not a silver bullet or something, but that's fine. We have to know why things can go wrong, why can things go wrong, and when things do seem to be right, what are the limitations of that solution? Okay, and I pointed out last time the fact that PVW form of the weak form allows functions that have kinks in them. This is the functional form that finite element methods uses. So the solution that you get from finite element methods has kinks in their displacement, which means that the strain will jump from one element to the next, even if your problem is perfectly smooth. And somebody might be tempted to think of some physical reason for why the strain jumps. There is none. There is a mathematical reason, because we have picked the space of that function to be in H1. So we have to interpret the results coming out of that finite element method accordingly. It does not mean that the finite element solution is wrong or inappropriate. We are using a model, so all solutions, all approximations are wrong. By definition, it's an approximation, that means we made an error. If you made an error, it's wrong. How wrong is it? That's your job to find out. Okay? All right. So, in short, we were solving that original strong form of the problem. We converted that to the weak form of the problem, and still we have just about an equally hard problem. We have not simplified it one bit. The simplification, as I've mentioned before, will come when we pick certain functions for real displacement and virtual displacement. Right now, all we are saying is what is the space of functions from which we can pick those functions. Okay. So if we solve the weak form, we have essentially found a solution to the strong form. If we have found an approximate solution to the strong form, if the continuity requirements of that function are satisfied. All right, so let me take a few examples of the displacement and all these different boundary conditions, which I think you are now pretty familiar with, having done some similar problems for the quiz also. And but what we'll do here is we'll write out this new terminology that we have established today of the essential boundary condition or the natural boundary condition or the homogeneous essential boundary condition. Okay, so all we are going to try to find out is what type of functions can we choose for real displacement and for virtual displacement. So let's see. For this problem, you can easily see that the boundary conditions we have at the left end is that displacement has to be equal to 0 at x equal to 0, or it has to be equal to u0. That's the given boundary condition. This is another thing that I saw, I think, on some of your problem 3 statements. In that problem, there was a spring and a traction at the left, at the bottom. There, at neither end did I specify displacement. Okay, so but in this case, I am specifying the displacement at the left end to be equal to 0. What type of boundary condition is this? It's an essential boundary condition, because when we pick real displacements, our real displacement functions must satisfy this. The weak form of the problem statement does not have any mechanism for it to satisfy this condition. So we must pick functions that satisfy this condition, and I'll show you how to do that in a very systematic way later on in chapter 6. But this is indeed an essential boundary condition, and the moment we have an essential boundary condition, you remember, if the displacement is specified here, the traction or the reaction is unknown, correct? Since the reaction T0 is really unknown at this point, we said that we'll pick a virtual displacement function that goes to 0 here so that we can eliminate that unknown traction. So as soon as we have an essential boundary condition at one end, we have a corresponding homogeneous essential boundary condition HEVC on the virtual displacement. So the essential boundary condition is on the real displacement. The homogeneous essential boundary condition is on the virtual displacement. Okay. Note that the real displacement could be non-zero, but the virtual displacement has to be 0, so that we can eliminate that unknown traction from the fixed or from the specified boundary condition. So that's the boundary condition at x equal to 0 for weak forms. For strong forms, you're already familiar with what that boundary condition is, so I won't go into that. At the other end, is that displacement or a traction boundary condition? Traction boundary condition. And with this new terminology that we use today, we are calling that a natural boundary condition, saying that traction is equal to FL divided by A, and by definition, traction is equal to stress at L acting on the unit normal at L, correct? This was traction at L is equal to stress at L acting on the unit normal at L. That's the definition of traction at L. And as looking at the way that I've drawn, FL is the force divided by area would be the traction, and it would be positive because it's pointing in the positive x direction. This, as I said, is traction boundary condition, which we have been calling natural boundary condition for our weak forms. And another reason we call it natural boundary condition, if you remember, is when we converted our MWR weak form to PVW weak form, we did integration by parts. When we did integration by parts, this natural boundary condition essentially fell out of that integration by parts, quote unquote, naturally. So it came out from the weak form in a natural manner. We call it natural boundary condition. There is no homogeneous essential boundary condition corresponding to this, because homogeneous essential boundary condition is corresponding only to an essential boundary condition. So that would be the only boundary condition at the right end. Okay. All right. Let's take this one. Traction at the left end, some specified displacement at the right end. So at x equal to 0, what would be the condition? Essential or natural? Natural. And we would say T0 is given to us. It is equal to F0 divided by A, since F seems to be pointing in the positive x direction. And by definition, it is equal to stress at 0 times the unit normal at 0. Right? That's my natural boundary condition at x equal to 0. And there's nothing else. The virtual displacement could be anything anything at this point. We cannot constrain the virtual displacement here or in the previous example here. The virtual displacement is constrained only here. On the right end at x equal to L, what's the type of boundary condition? Essential. So displacement, real displacement at x equal to L is given to me, UL, which is immediately an essential boundary condition, EBC, and there will be some unknown reaction here, unknown traction TL, correct? So to eliminate that, we will immediately say that the virtual displacement at L is equal to 0. That is the homogeneous essential boundary condition. Okay. So same problem, just flipped essentially. Just this, we are specifying the displacement here. We are specifying the real displacement here, which could be non-zero, but the virtual displacement at that right end has to be equal to 0, so that we can eliminate the unknown traction at the right end. Okay. How about this guy, fixed at both ends, or specified displacement at both ends? So we have essential boundary condition at both ends, no surprise there. U0 has to be equal to U0 at x equal to 0, which is an essential boundary condition, and UL at x equal to L is given as UL, that is also an essential boundary condition, which means immediately that I must pick virtual displacements to be 0 at both 0 at both 0 and L, so that I can eliminate the unknown traction at 0 and the unknown traction at L. So both of these are the homogeneous essential boundary conditions at x equal to 0 and x equal to L. So just to sort of give you some more pictorial view of what this would mean, it would mean back in this picture when we were picking the virtual displacement functions, we can pick only functions which go to 0 at x equal to 0, do something non-zero, and then go back to 0 at x equal to L. Okay. All right. So that's this type of problem which is fixed at both ends. How about this one? Type of boundary condition at x equal to 0. Natural. So T0 is equal to given force divided by area, and by definition is equal to stress acting on the normal. That's natural boundary condition. And at the right end, what type of boundary condition is it? Do I know the displacement here? I don't know the displacement here. So it's not, the displacement here is not given to me. I can find it, of course, but it's not given to me. So it's a mixed boundary condition, as we saw in the examples for those strong form also. And the way we find these things are, since we don't know the displacement at this point, we will choose the positive sense of displacement function u at L. Its positive sense would be moving to the right. If this end moves to the right, then the spring gets compressed, correct? If the spring gets compressed, it will push back with a force of KL times UL, correct? This pushback force due to the spring acting on the bar is pointing to the left. Therefore, the sign of traction corresponding to this would be negative, which means that the way that I would write this condition would be traction at L is equal to, from the definition, actually let me just follow this notation, it would be equal to minus KL times UL divided by A, the area of cross section, and by definition it would be equal to sigma L acting on the normal at L, sigma plus 1. Okay. So this is a mixed boundary condition, which again is like finding the unknown traction at this point, or the unknown displacement at this point. So this is not an essential boundary condition, which means that at neither end I have to choose virtual displacement to be 0. Neither of those ends had the virtual displacement has to be 0. So back in that space of functions, I could pick any function I want as long as it is in H0 for the MWR weak form or H1 for the PVW weak form. Okay. All right, one last example. This is problem with 2 springs, so both ends clearly are mixed boundary condition, and again going by the same logic, traction at 0 is if it moves to the right in the positive sense, the spring will get extended and it will pull back. So the force would be force due to the spring would be in the negative x direction, K0, and let me actually add the subscripts. This is K0, KL. So this would be, the force would be K0 here and KL here. So the traction would be in the negative K0 times U0 direction, divided by A would be the traction, and by definition that would be equal to stress at 0 times -1. This is a mixed boundary condition. And similarly at TL, it would be minus KL UL divided by A equal to sigma at L, acting on the normal +1. This is also mixed. Okay. So essentially, I mean, primarily you would have these types of boundary conditions. Either the displacement would be given to you, or there might be a spring, or there might be a free end where you need to find the real displacement. So it's either essential or natural or mixed. Okay. And as soon as you have an essential boundary condition, make sure you don't forget the corresponding homogeneous essential boundary condition on the virtual displacement. This is the most common mistake or oversight that I've seen in the past. But if you do that, then the solution that you would get from the weak form is always going to give you some number, some solution for it. But that solution won't be a valid or a meaningful solution. Just as a side note here, one could cook up a problem where I have some spring attached to some point in the middle of a bar. And if I do that, then that would be, you can see from this free body diagram, that the spring force, if I look at the displacement here, U0, the spring would be pulling back. So it's like applying a concentrated force somewhere in the middle of a bar, which means that the stress on the left and the right of the bar would jump. Okay, if you were to plot the stress function, we expect the stress function to be relatively smooth, because we also have to take the derivative of the stress function for our equilibrium equation. But in these types of problems, the stress would have a jump in it, and there are ways to tackle that with the weak forms by including a jump condition in there. But again, we will not go into those types of problems. So these are some common examples of boundary conditions for weak forms. The overall story is, I had a strong form, the form that you solved for your quiz 3. I can try to set up the same problem in a weak form, so that what we are trying to do now is that I can solve these types of equations, or these types of a problem where we have to pick functions for real displacement and some functions for virtual displacement. If I pick the right functions for this, there's no such thing as the right function, but if I pick good, appropriate functions for real displacements and virtual displacements, then I can get very, very close to the exact solution. Okay. If by happenstance I somehow pick the exact solution as one of the possible functions for my real displacement, then in that case I will get the exact solution from this weak form of the problem statement. But at least what the big upshot of this is that for strong form of the problem statements that we don't know the exact solution to, we have some mechanism now that will give us some approximate solution. Okay. So I think I have maybe very little time left here, but so what I'll do is I'll introduce this topic on variational methods, and then we'll leave it for after the Thanksgiving break to go into much more detail. So I'll also mention here that I'm in your textbook, I'm switching or jumping between chapters now. I'm including some stuff from chapter 9 into this because it sort of fits much more nicely here. How is this related to what we've been talking about with the strong form or the weak form of the boundary value problem is the following. You remember when we set up the strong form of the original 3D problem, we said divergence of stress plus body force is equal to 0. Can you tell me what was the physical principle that we used to come up with that partial differential equation?
Moments are
Forces. Right? So sum of forces equal to 0. Newton's first law. That's what we used to come up with divergence of S plus B equal to 0. S is equal to S transpose came from moments. So essentially what we did to develop the strong form of the problem statement was we used Newton's laws or Newtonian mechanics essentially to come up with the governing differential equation. There is an alternate way with which you can come up with the same governing differential equation from energy arguments. We are not going to use Newtonian mechanics or draw free body diagrams or do that sort of thing for that. We can approach the same problem from an energy point of view. And when we use what are called variational methods, as soon as you hear the word variational, try to associate that with energy-based methods. And here's a very quick example of that, and then I'll let you ponder about it through the Thanksgiving break. Here is what we did on the left-hand side is what we did to come up with the equilibrium equation that we set up. So if I have a mass and some spring, neglecting any dynamic effects, we can. The problem is that we want to find the displacement under the effect of gravity. So the force that would be acting on the mass would be mg, as you well know. If I draw the free body diagram, kd would be the spring force pulling up, mass would be acting down. That immediately gives me the equilibrium equation that mg is equal to kd. Therefore, I can find d is equal to mg over k. No surprise. That's just what we did. So think of this equation as divergence of S plus B. We used Newtonian mechanics, we drew a free body diagram, and we came up with the equilibrium equation. That was the way that we did up until now. The alternate way is to use a minimization of potential energy approach. Potential energy is equal to strain energy stored in the body, in this case that would be the spring, and the potential due to gravitational force. So strain energy stored in the spring, if the spring goes through displacement of d, would be what? If I have a spring, if I stretch it by d, what is the strain energy stored in the spring? Half kd squared. So half times k times d squared. And what would be the change in potential energy if the mass drops down by some amount d? If I have this mass, it has some potential energy here. If I drop it down by some amount d, the change in potential energy would be what? mgd minus, because obviously if I raise it, I increase it. If I lower it, the change in energy would be negative. So it would be minus mgd. And if I minimize this, so I will do partial of pi with d equal to 0. That gives me immediately kd is equal to, or kd minus mg equal to 0. Note that this is the equilibrium equation. So all we did was minimize the potential energy, and we got the equilibrium equation, which gives me back to the same. And actually, I should have written that here: kd is equal to mg, and that gives me back the same equilibrium equation. So even for our deformable bodies, divergence of S plus B equal to 0. For 3D deformable bodies, there is an alternate way to get to that equation using the energy approach, which we will discuss after the Thanksgiving break. All right, so let's stop here, and then I'll see you back in 10 days, and have a good break. And I'll see you back on whenever that is, Monday following the break. Yes, this afternoon we will still have a review session. Hope, how many of you cannot attend that review session? Okay, good. So I'll see most of you there. And we'll talk much more about this weak form thing, and I'll maybe even give you some future examples about how we can find approximate solutions. All right, so see you in a couple of hours, and if not, then on Monday.